Let's go ahead and get started. I promised you last Thursday we would get through the rest of this OWASP top 10, and I think we'll do so. And then we'll use today as the opportunity to kind of switch between this topic and the next topic. As we jump into the next topic, which is physical security, it's definitely an example of something that we can only do so much in the lab with our sort of entirely virtualized environment that we have there. But we make an attempt to do so. So you'll get to explore that topic this week in lab. But continuing on with our top 10, we are up to and left off at number 7, which, and some of these are kind of related. We already talked about one of the prior ones with sort of cryptographic vulnerabilities or implementation flaws. And this is related, but not exactly the same thing. This is identification and authentication failures. The idea here is that if you have some sort of incorrect implementation of authentication or session management, there could be some separate type of compromising of passwords, session tokens, or keys, and then there's some sort of identity failure associated with that. There's all sorts of ways that these can occur sort of separate and independently of issues with regards to the implementation of password security in the first place. If your system allows for either brute force or automated password attacks, like so-called credential stuffing, right? Where you take previously leaked username and password combinations and you just kind of attempt as many of those as possible. That would fall under this category. Versus the prior category was more about if the authentication mechanism was using a well-known kind of weak version of hashing or cryptography, it would be circumvented in that manner. Here, if your system just allows for attempting as many passwords as possible, that's a sort of separate but also well-known type of web vulnerability. Also, what falls underneath this category is just using sort of default or well-known passwords or account information here. That is still a very common issue that we see today. And then also falls under this category is just having sort of weak recovery procedures that themselves can be vulnerable to attack here. Some examples just provided by the OWASP folks. I just already mentioned credential stuffing. So if you use a list of known passwords, you need to have some mechanism in place to either rate limit or determine whether that type of attack is occurring. Just using plain passwords as a authentication mechanism is also no longer considered best practice. We talked a little bit about that last week. And related but not exactly the same concern would be how application session timeouts are concerned. You can log into a library computer and it tells you in no uncertain terms, please be sure to log out of this session before you leave. Depending on how that's configured, the vulnerability would be you're sitting down at a public terminal, you are accessing some web application, you believe you've logged out, you believe you've cleared your session, you've exited your session, but perhaps based on how that timeout parameter is configured, the next person who sits down immediately afterwards goes to that same web application and is able to log in with your credentials. Related but not exactly the same concept is that of session hijacking, where we have this kind of trade-off between the flexibility of TCP and this desire to have sort of stateful sessions via these web applications over HTTP. And there then needs by very nature to be something built on top of these TCP streams to keep track of where we are in a web application, to handle persistent authentication of users, basically be able to resume a prior session as we are potentially multiplexing all sorts of TCP connections across multiple users. So there is some mechanism, some session token. It could be encoded directly in the URL, and you do see web applications that just encode it directly in the URL. Could be stored in cookies, which we see, or in some sort of HTTP header information. That itself is still, any one of those options is still valid practice and common practice. Where the vulnerability comes in is if a user can either directly intercept that session information, or more commonly, if we don't have some sort of proxy or man in the middle in the connection, if the attacker can predict and guess what future session tokens would be. If it's a really kind of simple algorithm that just increments the token from one user to the next user, you look at your own token, you can then predict what future tokens are going to be. Then that token is effectively being leaked in that way. Similar to how we are encoding passwords, if you don't use some sort of cryptographic, effectively randomizing approach to generating these tokens, you are susceptible to session hijacking. Ways we can prevent these attacks in general, of course, following best practices and not just entirely relying on passwords and having multi-factor authentication, making sure that we don't have sort of default credentials, or if we have them, required that they be immediately changed upon initial login. Testing any new passwords against one of many different lists of either leaked passwords or worst passwords. There are all sorts of public databases for these informations. We saw prior databases that were more about just big dictionary lists or rainbow tables that can be generated. And this is related to this. By clearing one or many of these lists, one can pretty quickly determine that if a password that someone has selected is appropriate or not for your purposes. You may find that as you're logged into your web browser and you attempt a password for a web application, depending on which web browser you're using, what settings you have, it may tell you, this password was located in a breach, you should change this. And it's doing so by effectively doing a centralized lookup of one or many of these databases of known passwords, default passwords, or just commonly found passwords. They're kind of interesting to look at. This is the top 10,000. I want to make sure I get this phrase exactly correct. Worst passwords. Worst is a funny thing. It's a little bit different than most commonly occurring passwords, for which there's also lists of those as well. I think the two terms are closely related to each other. If a password is commonly occurring, it's likely to also be a bad password as well. I'm actually not certain how this list gets generated, how they determine whether something is the 5,000th worst password or the 5,001st worst password. One thing we did look at is those automated password cracking utilities, like we looked at John the Ripper and you played with it in lab. One measure of quote unquote, badness or relative worst ranking of a password would be, how difficult would it be for a tool like that to be able to crack it? But that definition is a little circular, right, between common passwords and worst passwords, because what do we see that those tools do, at least sort of in the default algorithm, is they look at word lists, right? They look at word lists and lists of known common passwords and attempt those first as kind of the low-hanging fruit of password cracking. So common versus worst, it's a little circular, but I guess if your password shows up on this list, it's sufficient to say you should change it. It shouldn't be one of the passwords that you would be using. I checked, and Hunter 2 is not in here, but Hunter is, and so that counts. And really just mostly common words, just common patterns. Basically the passwords that people would use if you're requiring them to use passwords, but you're not providing any sort of additional restrictions on what passwords are valid or not valid. So in terms of policies that one can implement in a web application to prevent these kind of failures, that's one thing that you should do. There are automated ways to effectively do that lookup and say, even though it doesn't technically fail a other password policy we may have in place, like NIST 864B, it's in this list, and so we shouldn't be using that password and letting users know that they need to select a different password. And we can quickly look at those guidelines for what they call memorized secrets. It is an attempt to standardize both a little bit of what cryptographic flavor should be in use for securing the secrets, as well as an attempt to provide a broad enough set of recommendations for what would be allowable as passwords in a system. And this is beyond just web applications, but is relevant for web applications as well. Uses that kind of spec formal language, but verifiers shall require subscriber chosen memorized sequence to be at least 8 characters at length. So if you ever set a password and it's saying you've only selected 7 characters, and it's not sufficient, well, that would be potentially because that system is attempting to adhere to this particular standard here. And verifier should permit subscriber chosen memorized secrets at least 64 characters in length. That's a pretty long password. I don't think I've ever used a password that long. In fact, usually I run into the exact opposite issue where the password, which must be between 8 and 11 characters, and that kind of limits the range of the type of passwords I like to come up with and use. Claims that Unicode characters should be accepted as well. That is not universally allowed, but a lot of systems do allow Unicode for characters, and we'll talk about Unicode a little bit in more detail in a couple weeks because it is very relevant for what we're doing here. So in terms of what other things shall or shall not be allowed, should compare against a list that contains those bad values here. Easier said than done, as the size of these databases of have I been owned type databases are growing and growing, but it's something that can be checked. And you will find that most web browsers, as they implement web application front ends, do that sort of checking. You've attempted this password. It technically is allowed based on the other requirements that are in place, but separately it's checked and it shows up somewhere else. Dictionary words of the list we looked at, or things that basically otherwise would fall into that algorithm of password cracking. So it looks at commonly used words, looks at commonly found passwords, and starts to also, as we saw, do kind of basic things like modifications of username or derivatives of the usernames here. So in terms of preventing that, it's really not a binary thing in that one can implement a policy that would guarantee that there's not going to be any identification or authentication failures, but ways to kind of mitigate the potential aspects there. Number 5 is an interesting one, and if you look at various web applications, you will find that this is not universally supported, which is providing the same exact identical error message when either the username is valid or when the password is wrong. Why would we want to implement that? Or why would web applications want to implement number 5? Sure.
If somebody's trying to brute force a password and they don't know username,
And it is related to exactly right. So it's related to credential stuffing. So just to repeat what you said here, it's in a sense related to number 6. Limit the number of failed login attempts. But with number 5, no matter what is wrong about the login attempt, we don't want to inadvertently sort of leak that information to a potential hacker, right? It can be frustrating as a user. You're going back to a web application you haven't used in 2 months, and you're trying to remember what your account is and what your password is. So it's a little bit frustrating there that you don't know if they implement number 5 properly. Was my username what was wrong? Do I have to do @gmail.com, or is it just the username? Or was it my password that's wrong? But if we don't implement that, if we have a separate error message for username is invalid versus password is invalid, then in fact our authentication is actually leaking quite a bit of information. And when combined with number 6, where you potentially don't have a limit to the number of failed login attempts, typically the username space is going to be smaller than the password space, depending on the number of characters allowed and things like that. And if we don't have that, then potentially you could be leaking all the valid usernames for a particular application or service. And finally, number 7 is, and although we just kind of hand waved our way through that this idea of having some sort of session ID, whether stored in a cookie or directly encoded in the URL, is appropriate and valid. That has to be a sufficiently random piece of information, because if it's not, then that is also leaking quite a bit of information. If someone can predict, if someone can guess what the next session token would be or what prior session tokens were, then you have a definite issue in which, without even needing potentially any authentication at all, someone can subvert an existing session. So that's number 7. Number 8 is a little interesting. I stole this GIF shamelessly, but I like it. This is software and data integrity failure, which is also related to, I think it was AO4, where we were talking about maintaining and security of plugins and the fact that you may be able to audit your own application, but the plugins that are built on top of it may be a much more big of a challenge to do that kind of auditing. This is related to this, but it also has to do with software updates, data that is stored as part of your automated software build and deployment process, and whether or not those processes are properly verifying the integrity of your build, as well as your artifacts, as well as your actual application that you wind up deploying. And I think this is on the list because it just wasn't really thought about at the time. And so I do wonder, as we start to look at the next list coming out this year or maybe early next year, whether this would stay on the list. So the idea to start with, we have these continuous uh, integration, continuous deployment pipelines here. If you've done some more advanced software development, you may have played around with this kind of technology. The idea is you make some change to your code. You're working on a code, you're collaborating as part of a team, you commit, you push that change to your code. That's what's shown here in the kind of mesmerizing little um, assembly line GIF going on here. We're already doing that as we're working and collaborating and building code. The idea of this pipeline, yes, the idea of this automation pipeline is as you do that committing, that pushing of your code here, that then kicks off an automated or semi-automated process that then builds the code for you. That may be a different experience than those of you who perhaps are not in software engineering or haven't taken some of those courses yet or are planning on, where in your experience, probably everything is very local, right? You're editing a piece of code, you save it locally, you build it locally, you execute it locally, and that's still a valid approach. But in this more, I think, more common approach, certainly a more common approach for web applications, as you are saving that code, as you maybe already tested it locally, you then push your changes to the code, and there's some automated or semi-automated process that takes those changes and integrates it with the rest of the code that's recently been pushed by you or by other developers. And it does some sort of automated testing on some deployment server. And at that point, it's kind of a binary result. Either you push some code and it passed all the tests that were put in place, in which case it continues to the next step, or you get some sort of error message or some sort of issue, and you get some sort of result that says, well, you've made this change, and now test number 323 fails. And that's usually then on either sort of a dedicated deployment specialist to handle, or you as the developer to handle, where I've pushed a result, it has broken something, I haven't actually succeeded in whatever task I thought I was actually working on at that point, or my fix to one issue created some other issue. Modern software development is complicated. That is a pretty common feedback loop in code deployment even today, where there's that kind of automated testing and integration infrastructure. On top of that, that's the CI for your continuous integration or continuous improvement. You then have the continuous deployment as well, where as part of your development, as you're making some change and you have some web application or other application in production, as you do that build automated testing process, there's then all the remainder of sort of the packaging process that may have to happen, such that users who go to your website would then actually see the updated version of your web application and be using that in a continuous fashion, versus other more sort of traditional software where there's an update to the code every month, every 6 months, every year, however long it needs to take. Here you have a more continuous process that every time someone pushes a change, there's some automated tools that allow you then to build the resulting application and potentially deploy that application to production. That is all in all a very nice thing for modern software development. It's got a little bit of cognitive overhead associated with it. If you're used to just kind of working on a single code editor by yourself and testing everything locally, going from that to understanding some of this whole build process, it does take a little while to kind of get used to and comfortable with. Once you're in that steady state, though, it's a very nice place to be as a developer. You've made your change. You instantly get that feedback as to whether or not your change is breaking other people's code or breaking other expected functionality. And then if everything gets greenlit and passes all the tests, then you get to see your change kind of deployed immediately. It turns out, and again, to what extent this will continue to be perceived as an issue for future updates of the OWASP, that this kind of infrastructure was also not really built with security in mind, at least not originally. That this process is itself a series of generally publicly available servers. This is likely a publicly available server. This is a publicly available server. this is likely a publicly available server. And consequently, if there's some vulnerability in any of those services, you wind up with kind of very difficult to track down vulnerabilities in which your actual build process itself can no longer be trusted. That you yourself may have written code, or your team has developed code that is following appropriate design patterns and implementing authentication correctly and following all the best practices that we've talked about. But then at some part, there's an insecure staging environment, build environment, deployment environment that is itself going to insert default passwords or insert some other sort of well-known vulnerability into your code. That can be a very difficult thing to track down because then it's really about trust in your own tooling that you have to be concerned about, not so much the trust in your own code that you are writing. And the general workaround is not a very straightforward thing and is not something that we generally deploy on a day-to-day basis today, but it's doing some sort of integrity checking or signature checking of your application itself. That it's not just the code that we're auditing and being concerned about, it's not just all the network and other system configuration, but it's the actual deployment of the application itself. Can we use cryptographic and other corresponding techniques to provide some sort of signature for the application itself so that a user can say, okay, I have some reason to believe that this application is the one that the developer claims it is and that it hasn't been modified at any point along the process. It turns out to be a difficult thing to do in practice. Also falling into the somewhat broad category of software and data integrity failures is something we've talked a little bit about already. We'll talk about it a bit more, which is sort of supply or software supply chain attacks. This has to do with your plugins or your libraries and modules that are potentially coming from untrusted sources or repositories. Modern web development is module upon module upon module. The goal being that you as the developer are writing perhaps as few lines of code as possible. Sometimes in some configurations, no code at all, and you're just configuring existing modules. But then underneath all that is all sorts of usually open source, oftentimes third-party modules or libraries or plugins that are what make the entire web application work for you. That itself is a potential vulnerability. Some of the examples they provide, the first one just has to do with having an update to a piece of software that doesn't involve code signing. We won't talk much more about code signing in this class, but the idea being that just like with our password, we're also, we're storing this hash value that gives us some reason to believe that if the password changes, the resulting hash is very likely to change. It is effectively doing the same thing with regards to our applications themselves. We are saying, here is my 7 megabyte executable that's going to become part of your web application. Here is now also effectively a signed hash value that says, if anyone changes any of those bytes in the executable, the resulting SHA-1 or other hash function as applied to it will lead to a different result that gives you some confidence that no one has messed with your application. In practice, that does happen in some environments. Certain application stores require some sort of code signing for any sort of deployment, but there's all sorts of other scenarios in where that is not expected, that is not the default. And firmware for Internet of Things devices is a very common example where the expected fix, if you have some sort of bug in your firmware, is to go to this arbitrary website, is to download this binary blob, and there's a lot of trust involved in that entire process. With the update mechanisms themselves potentially being part of the vulnerability. I won't talk anymore right now about the SolarWinds attack. It's something you can read up on, but it was basically subverting the build and deployment infrastructure of the type I was talking about and illustrating on the prior slide here. Not even necessarily messing with the original code itself that was being built, but the actual deployment of the final executables themselves were being subverted by taking advantage of that CI/CD, effectively that same type of pipeline here. And scenario 3 is related to kind of exposing public data as part of a programming paradigm. It's a little bit far afield from the other two examples, But in terms of software supply chain vulnerabilities, there are many such examples, and actually more of them happening every day, such that if I had to predict this focus on uh, continuous CI/CD pipelines is probably going to be less of a factor for future versions of this top 10 list, but this issue of software supply chain security will probably get called out as its own separate thing. And those of you in this class have different backgrounds, different levels of experience in programming. Um, Depending on what classes you've taken or what projects you've worked on, this may or may not ring as true to you. But this is an example, and just one such example of a very popular NPM package. So the Node Package Manager for writing basically server-side JavaScript, which is used for all sorts of purposes in web applications. Again, that is an example of a programming environment where the design philosophy seems to be, let's write as few lines of code as possible to hit our functional goals. Let us reuse as many existing modules as possible such that my code becomes a lot easier to read. It's just fewer lines of code. The resulting code does wind up being more expressive than if you have to implement every little thing yourself from kind of base vanilla language. The flip side of that is that you have this ecosystem in which all sorts of what would otherwise be kind of basic built-in functionality of the language is instead effectively outsourced to this set of untrusted, unknown third parties who build and support and design these various packages that you are going to use. This example is for a piece of software that's attempting to do proxy auto configuration, and it's a necessary feature for web applications. And it turns out for this particular package that had over 3 million weekly downloads, and that's a little misleading in that every time you want to do a fresh build of your Node application, it's going to do a fresh download of that. So, but still, it's something that's was commonly in use, commonly being integrated, commonly being built into application, turned out to have itself a pretty serious flaw in it. We talked a little bit, I think that happened more on Discord than on class, about another JavaScript package that was in very common use. And again, people rely on this. That is kind of the state of the art in doing modern JavaScript programming. And when you don't necessarily have a way to audit those existing packages, when there is a third party that's kind of hosting them all, but no one who's performing auditing for whether there's malicious actors, whether there's just traditional vulnerabilities in those packages, you wind up with a software development methodology in which you really can't trust the end result. That's just one example of so-called software supply chain, where you're building software and you don't really have much trust in the underlying components. There's several dozen such examples. I expect this to be considered a bigger issue in future iterations of this top 10 list. And for that reason, option number 2 here is actually quite difficult. So use trusted repositories for any external libraries or dependencies. That's one of those things that sounds good. Okay, just use trusted repositories, don't use untrusted repositories. But that gets into the nature of what is trust, how do we develop trust, how do we establish trust with regards to external libraries or dependencies. And it's one of those situations that's a little recursive as well. You may have established that this repository is a known trusted one. It's developed by an established software company that is expected to have certain levels of quality and standards, but what libraries are they using under the hood? And to what extent are they not entirely reliant on trusted repositories all the way through? That turns out that in modern web application practice, for development practice, that turns out to be a very difficult thing to really, easy thing to say, difficult thing to actually guarantee. And then number 4 becomes very important, which is we have these very nice continuous integration / deployment infrastructures in place. Are they separately themselves being audited for security considerations? Are they themselves treated as a potential entry point of attack into your system, into the actual code that you yourself are building, integrating, deploying? That's something that there's a lot higher awareness of that now than there was previous to this list coming out. And so we'll see if it's still considered an issue going forward. We'll get through this. Number 9 is security logging and monitoring failures. And here, potentially, the issue is just the abundance of logging and monitoring data that a typical system is capable of producing. Um, and whether it's failure to log and monitor logs, or is it the failure to detect malicious activity within logs? In practice, it's been shown that a breach occurs. It could have been detectable instantly. The evidence available to detect that it happened is there available instantly, but it takes some period of time between actual breach and actual detection of breach. Not necessarily because there is no logging or auditing of logs, but because whatever logging, whatever warning and error message that are coming are being reported, and no one's actually responsible for doing that sort of secondary reporting upon initial error logs. And it turns out that that is not an easy problem to solve. That if you want to have an intrusion detection system that is determining what kind of activity is happening, you are generating tons and tons of data through such a system, the vast majority of which is not interesting, the vast majority of which is noise that could potentially be discarded. And it turns out the solution for this tends to be that there has to be sort of separate tools and tooling, and probably security engineers whose job is to be responsible for managing those tools and actually doing active auditing of the logs in your system here. In terms of the examples of failures, these are just breaches that weren't detected in a reasonable amount of time for the most part in these 3 scenarios, because there was really no one whose primary responsibility was to do that type of audit of security logs here. Again, it's one of those things that sounds easy in practice. Well, why don't we have someone doing that? It's not necessarily the case that it's immediately obvious from a log what the actual intrusion could have been, and you're also potentially having to build infrastructure and resources dedicated to doing that type of auditing, because the amount of data one would be pouring through can grow quite significant in a period of time. Again, similarly, the solutions or ways of preventing this are a little bit rosy here. Um, you typically need in a larger infrastructure, larger corporation, you need to have some sort of log management, log auditing system, separate from just relying on a Linux system or Windows system administrator from also taking on the task of monitoring logs and determining if something bad has happened here. There are all sorts of softwares, either big commercial ones that attempt to solve all problems for all people, or sort of open source one-off softwares that are useful for doing one particular subtask of continuous logging and monitoring of logs. Fail to ban is one that people have used for many, many years, where if there's too many failed log attempts, it attempts to block connections from a particular IP address. But in general, I would say this is not a solved problem, because as more and more advanced tools for transaction logging, network logging are available, as we have the ability to basically log and store relatively low-level information from application level almost all the way on down, there needs to be mechanisms to kind of keep up with those data streams. And I would say that's not a solved problem. And it's really more of a matter of how much are we dedicating resources to this problem versus treating it as kind of a cost, kind of a negative for an organization to have to deal with. Possibly an area in which either centralization or existing legal frameworks are possibly necessary to be able to really support this problem. We talked a little bit about the regulations one has to follow if you're handling personal information in Europe, at least, or if you're handling credit card information basically anywhere in the world. Those are the kind of things that are attempted to be encoded in regulations. In practice, these issues still happen on a day-to-day basis, but it could be the case that for this, the solution is more of a regulatory/legal framework mandating or enforcing that certain policies are in place at these organizations, versus there really being first and foremost a technical solution to the problem. And finally, this one's a little interesting to me. Again, we talked about whether this list was truly kind of sequential in terms of importance. This one's very specific, I guess, versus the first 9, which encompassed a lot of different other things. This is server-side request forgery. Now, if you were to look at prior versions of the list, there were also separate one-off attacks that were listed. The prior version listed cross-site scripting as a specific top 10 thing, and now it's still in the list, but it was part of that just code injection attack, AO2 or whichever one that was that we covered last week. But this one is separately listed as a concern. Whether it's the flavor of the moment or whether this is an ongoing concern is hard for me to say about this one. Also, what can be a little annoying about this, and certainly if you look at our recommended textbooks for the class, you'll see this description here, is that there's a little bit of a subtle difference between very similar sounding and really looking things. And I kind of debated to myself, how important was it for you as a class to know what server-side request forgery was versus a client-side request forgery versus cross-site scripting? The truth is, they make good quiz questions. So if you to know the difference between the three. And they're also very similar. So I think having awareness that these are related but slightly subtly different things is probably sufficient. This one is in the top 10 in and of itself by itself, so we can cover it in a little bit more detail here. But we had previously covered cross-site scripting a little bit, right? Cross-site scripting is when you have some sort of text field. We did this last week, right? And you did it in lab as well. You have some sort of text field or some user modifiable input as part of a web application. And if you don't have, input sanitization, right? If you don't have input checking that's determining and filtering and saying, is this code or not, then you can have all sorts of scenarios in which a user can input basically code into your web application. The examples we did were pretty straightforward of get it to pop up an alert box in JavaScript. In lab, you had it read from files in the system and then also attempted some remote shell type of thing, reverse shell type of things. That's XSS, or sometimes called CSS, unfortunately, cross-site scripting. That is client-side still. That is the user directly being able to modify the input into an application and the flaws in the application front end itself, because it's not sanitizing input. It's letting you input all sorts of stuff. So that was AO2 on this top 10 list. We had also briefly talked about CSRF, or client-side request forgery. That one's going to come up a little bit later when we talk a little bit more about social engineering and you kind of social engineer yourself in the lab. There, it's where you have some malicious third party that effectively is attempting to trick a user into unknowingly submitting some request to a web application that they themselves did not intended to do. So you have a user who's authenticated into a web application, they're logged in for want of a better word, and you then trick that user into clicking a link that withdraws money from their bank account or sends an email or does something. That involves some sort of other mechanism in which you get the user to do something they were not intended to do. And there's all sorts of ways in which that can be made quite clever through social engineering as well as some technical approaches that basically is tricking users into doing things and exploiting the trust built between the user and the application as well as the application and the web browser, or the user and the web browser, that kind of existing trust. Exploiting that, it's all still happening on the client side then where the vulnerability is. That's called CSRF, or client-side request forgery. That is then similar, but different, to server-side request forgery. Here is where the web application itself is being tricked into doing something internally that was not originally expected to do. So we can start by looking at this very high-level flow chart, and I have a link showing what happens here in practice with this sort of silly demo here. That you have some existing web application that is part of its design, and we had that big picture view in the very first slide here, whereas part of some request that's provided to the web application has to do something internal, right? It has to grab data from the database or run some code on some other internal service in our system here. The vulnerability then would be here is if a malicious user, can sort of trick or convince this web application to access things it wasn't originally designed to access internally. And the reason this is considered a separate thing from just general, software vulnerability, common weaknesses in software, is because oftentimes a system is designed such that you have everything external to the network and everything internal to the network. This is meant to kind of indicate sort of a firewall here. And once you're inside the network, there's this level of trust that, okay, I don't let external users access my internal servers. They can't probe them. But once I'm already inside my network, there's no harm there. We allow that to happen. And so what happens is that if in practice, there aren't enough protections to limit what this web application itself can potentially access on your network, then all sorts of additional information can be leaked out that wasn't intended here. This is somewhat inherent in the nature of how modern cloud services are built and appears to be an issue that occurs in all sorts of modern scenarios here. You can take a click on this link as well if you want to follow along locally on your own machine, just by clicking on the link in that slide in the PDF on Canvas. This is kind of like a lab-like environment. This would be a difficult thing for us to build directly with our lab infrastructure, but it's meant to show how kind of by nature that you have a web application that needs to potentially, in this case, access some cloud services. So there's already a required kind of connection between the web application, data that the user is passing to the web application, and potentially some information that we wouldn't potentially want leaked back out. That all sorts of things can be happening that look kind of similar to our cross-site scripting, but aren't the same because we're not tricking the client side of the application. We're tricking the server side of the application to return or access things that it otherwise was not designed to do here. But kind of like our lab examples here, it's fine, but it's also kind of synthetic in the sense that it works exactly as expected, but the real world will not nearly be as clean and as neat here. So what happened in this example, you have a curl request. We were playing around with wget, but it's a similar concept. We're wanting to grab a web resource. This is akin to opening up a web browser and doing a GET request at this particular URL. And in this case, it has some sort of internal web application. Once we reach resource named image, it then takes a parameter that provides a URL that we want to access it. And in this case, we already have some reason to believe that there's an SSRF vulnerability here, that this was meant to access a particular image. We instead ask it to access localhost. That localhost would be the local host of that particular server, whatever's locally running on that web server. That would be a potential indication that there's already some sort of issue here. For the most part, I'll let you guys, you can access this link and run through this example here, but just to show the next step of what happens here, playing around with it, exploring it, one may have some knowledge or find some ways to find out more information about what's happening on that local host that this server is connecting to. Perhaps there's an additional administrative interface running on port 5000 that is only intended and is only designed to be accessible locally. Again, this is a synthetic example. You may have some reason to believe that for certain common configurations, there would be an administrative interface available on port 5000. This example is synthetic and kind of made up, but if you know something about the web stack or other underlying technology of a web application or organization, you would have reason to be able to do that type of targeted digging here. And again, the design flaw is not necessarily in this particular server that has something running on port 5000 that is designed to be only sort of locally accessible. Again, if we go back to this diagram here, it's some internal resource that's designed correctly to only be accessible locally from other things on that same network as it. But we have this web application that also needs to be able to access the internal network. Again, by design, that it needs to be able to access a database or other web services running internally on the system here. And if there is this flaw in which we're not really doing a filtering or sanitization or checking of what resources we're allowing to access, we now have admittedly synthetic, but potentially real example in which we now have some sort of administrative portal that is now accessible to anyone who has access to that public-facing web service. Which, of course, if we were to look at the HTML that gets generated, click here for users, click here for password reset, click here for logs, then presumably that would be the next place you'd want to look, right? You look at that localhost administrative site running on port 5000, then whatever the user's subdirectory is associated with that, and now you get some additional information of administrative contact information and things like that. That is one example of server-side request forgery. If we have some sort of cloud instance, some well-known cloud instance that is part of that infrastructure, it's not really shown here in this diagram, but the assumption is that this web application may be accessing kind of internal resources, but by the nature of modern web applications that have to scale to thousands or millions of users, you would then be also needing to access external public-facing cloud resources. So that arrow would be kind of going off here somewhere. That it turns out that if you have any knowledge about where those resources may be located, you can then use a similar type of vulnerability to expose those things publicly that were never intended to be exposed. If you have an EC2 instance, I actually don't know how globally true this is, but we can kind of play around with it. A common IPv4 address space for an EC2 instance would be the following. So that example is partially true and sufficiently true, or sometimes the application will have a local DNS entry that will allow you to access where it's going to be located. In this case, server-side request, we were asking for an image, but instead we're asking for whatever is running here on our cloud instance. And if you know enough about AWS, you can learn things about what security credentials you have associated with the user there. Again, this example is kind of synthetic and silly. It's meant to be like our lab-like environment here. But in practice, exposed EC2 nodes is a very common web application vulnerability. The application is designed such that only things internal to here can access all your secure data. But in practice, you have some sort of web application that is responding to input. And similar to the client-side requests where we're accessing things we weren't expected to be able to access on the client side, here now on this side, we are passing things and accessing and returning data back out that we weren't expected to do on the server side. They're similar in terms of the impact, but the vulnerability is kind of different, and the actual kind of workarounds or preventative measures wind up being different as well. In practice, to really prevent against server-side request forgeries, there has to be some sort of HTTP proxy on the server side as well. I won't get into too much detail of what that would look like in practice. There needs to be someone else, another adult machine in the room in this diagram here to determine, effectively acting as an application level gateway, saying, by default, we assume that everybody can access everybody here. Let's actually limit those rules and prevent what HTTP calls are going to be allowed, even from otherwise trusted endpoints in our system here. You can think of that as an HTTP proxy internally on the server side here. Otherwise, what is considered, best practice in network design is applicable here also, which is, segmenting into separate networks and only having kind of singular connection points as needed on an application by application basis. That becomes a very difficult thing to do when you have both sort of internal resources as well as cloud resources. How you maintain that kind of separation becomes kind of difficult. And then otherwise, best practices in network security and firewall design are important things here for this as well. But at the application layer, depending on what your application is intending on doing, I say sanitize and validate all client-supplied data. That actually becomes a much more difficult thing for server-side request forgeries. If you have a web application that does expect there to be server-side requests that are valid, you either have to explicitly whitelist or you have to be very careful in the design of that sanitization and validation scheme here. Let's leave things here for today. Please come back on Thursday. We'll start talking about physical security. It's kind of a jump, but I think it's a necessary jump. We'll look at some more real-world aspects as well.